Hi. In this first presentation of the regular sequential circuits playlist, we will look into the basic concepts associated with this class of circuits. At the end, I hope that you will be able to explain what is the distinctive feature of sequential circuits in general and of regular sequential circuits in particular, and also that you will be able to create VHDL descriptions for regular sequential circuits. The presentation itself is organized into three parts. We will start by sequential circuits in general, then look at the specific case of regular sequential circuits, and to close we will consider the most common regular sequential circuit structures. So, what is a sequential circuit? The distinctive feature of sequential circuits, whatever their specific type may be, is that they are able to store information about past events. They do so in the form of internal states, and the outputs will depend not only on the current input values, but also on the internal state of the circuit. This explains why, contrary to what happens in combinational circuits, sequential circuits may exhibit more than one output pattern for each input pattern. The universe of sequential circuits is much wider than what we will consider in this course, and particularly in this module. To start with, notice that information about past events may be made available by introducing feedback, for example in the form of bistable latches that toggle their state. These circuits do not need a clock signal and as such are normally called asynchronous sequential circuits. The alternative is to use clock-driven storage elements, normally in the form of edge-triggered flip-flops, which are organized into registers created to store state information. We will only look at synchronous sequential circuits where the flip-flops share a common clock signal. Synchronous sequential systems are normally represented as shown in this slide, comprising a state register in the middle holding this state information and two combinational logic blocks, the one on the left implementing the next state function and the one on the right implementing the output function. The next state combinational logic block on the left is driven by external inputs and by the internal circuit nodes holding the present state information, and defines what next state the circuit will move into at the next rising edge of the clock. The output combinational logic block on the right is driven by the present state nodes and defines the external outputs. You may have noticed that there is a direct connection represented in a different color from the external inputs to the output logic block. The reason for using a different color is that this connection may or may not be present, as we will see later in more detail. If it is present, then the external outputs can change at any time, since it is unpredictable when the external inputs will change. However, if the orange connection is not present, then the external outputs will change synchronously with the clock signal, since the present state changes with the rising edge of the clock. The circuit state, as we said, is defined by the outputs of the state register, which are updated at every rising edge of the clock. It is important to realize that the number of states and the state transition rules are derived from the functional requirements that guide the design process, and that this task of converting the functional requirements into a formal state transition diagram is critical and is actually a frequent source of design problems. So far, we have spoken about sequential circuits in general, but the specific topic of this module is regular sequential circuits. The distinctive feature of regular sequential circuits is that they have predefined state transition diagrams and output behaviors. In other words, the combinational logic blocks are predefined to implement commonly used functions such as simple registers, binary counters, and shift registers. By now, it should be clear in your mind that regular sequential circuits are seen here as a subclass of synchronous sequential circuits, which in turn are a subclass of sequential circuits in general. We will still consider another type of synchronous sequential circuits in the next module called finite state machines. For now, let's look at three representative types of regular sequential circuit structures. The first type is the simple state register, which is the type of block used to hold state information in the block diagram that was presented earlier. You may wish to pause the video for a moment now to look at the code, and particularly at the architecture section. Notice the rising edge condition that we will use extensively in this course, and also the use of a process to enclose the if statement. How would you change this code to support an asynchronous reset input? Vivado Synthesis generates this generic technology model and estimates that the number of cells needed is equal to the number of bits. Why is that so? Another very common regular sequential circuit structure is the shift register. May I recommend again to pause the video for a moment and try to find out what specific type of shift register is this one. Does it shift to the left or to the right? And here's the generic technology model created by Vivado Synthesis. Do we see feedback represented in this diagram? Last but not least, since counters are so often used in digital circuits, here's the VHDL description of an 8-bit binary up-down counter. Notice that the state register code in the architecture section is exactly equal to the shift register description. How is this possible? And why is typecasting needed in this case? Okay. I guess that you will need to pause the video once again. This diagram shows the generic model representation created by Vivado Synthesis, where you can see the adder and subtractor blocks used to implement the counting function. And that's it for the introduction to regular sequential circuits. Thank you.